So I'm going to cover 6.1 and 6.2 today, and we're basically going to do homework. We're going to practice today 6.1 and 6.2, and then also on Tuesday 6.1 and 6.2, since we don't have classes on Monday. Okay. But the reality is I'm going to go through some just basic rules for 6.1 in terms of antidifferentiation in indefinite integrals. And these are the basic rules, and then we'll get into some more complicated stuff for 6.2. This is just a general review. we're not actually going to do any problems for 6.1. Okay, this is on page 120. This box is on page 120 in your workbook if you want to just screenshot from there. But I'm just going to go through all the little rules just as a reminder or refresher, and then we'll just start using them in 6.2. So the power rule, of course, remember that it's called antidifferentiation because integration and differentiation are inverse kind of operations. So when we're working the power rule for integration, we kind of work it backwards. With derivatives, the powers always go down. Well, with antiderivatives or integrals, the powers go up by 1. So, of course, this is the power rule. You add 1 to the power, and then you have to divide it by that power, whatever that new power is. Or you could multiply it by 1 over n plus 1, right? These are, I'm going to fly through these now, okay? So the constant rule, if we have a constant, the integral of a constant, then it's just the constant times x. Don't forget about the c, okay? Because there's always an additional constant that you have to tack on when you are finding an integral. And that has to do with shifting on a graph. That we talked about it when we were doing chapter 5, that it could be a vertical shift. That kind of represents that. Eventually, in 6.1, you have some problems where you will find the constant. You have to be given some information in order to do that. So if you have a constant, then it's just going to be the constant times x, assuming that we're integrating with respect to x. This can be different too, right? Then we have scalar multiplication. So if you have a scalar, a constant being multiplied by some function, that constant can come out in front of the integral and we can ignore it, okay? Constants can be factored out, but you can't throw a variable out there. This is only for constants, okay? Sum rule, so if I'm taking the integration of a sum, you can treat them as the sum of 2 integrals. Exponential rule, we've got the integral of e to the x is still e to the x. And then again, we're working these backwards. A to the x is the same as a to the x over a natural log of a. And then you have all your trig rules. And I didn't put them in. Or maybe I did. Oh yeah, no, because I want to go through them with you. So actually you fill those in. Let's do that. Fill those ones in there, and let's see what you end up with. All right, who wants the easy one? All right, Ava, what do you got for the integral of cosine? Just straight up sine x? Sure you don't want to add anything? Plus c. Don't forget your plus c. Okay, so all you guys forgot your plus c. That's really easy to forget, but you gotta always have it. You gotta have your plus, you gotta have that constant, okay? All right, the next easiest one. Who wants it? None of you you want more of a challenge?
I'm not sure about my easy ones apparently. So.
Oh, well just because you left off the plus c, it's okay.
Can I get?
All right, just go ahead, sine of x. Okay.
Oh, that's not the one, okay.
Yeah, we're going across. Is that right? Is it negative cosine or is it cosine? Negative.
Yay!
Okay. And if you aren't sure, what can you do to be confident in it? Take the derivative of it, right? Take the derivative of it. All right. The next one should be easy. Yeah, tangent x plus c Who wants the next one? Cosecant squared. No, you can't go again. Grant, what do you got?
Oh boy.
No.
Is it cosine x plus c?
What do you think? Do you guys think he's right?
What do you say?
What do you?
Cosine x plus c
I think it's negative.
is it negative?
Oh my God.
All right. So now these get a little trickier, right? Because you have to remember your trig functions. Who wants the secant tangent?
Secant x plus c.
Say again.
Secant x plus c.
Secant x plus c. There's only one left. All right, Soph, what do you got?
Negative cosecant x plus c.
No, negative cosecant x plus c. Okay. Now, if you didn't remember all those, I understand. Hopefully you remembered the first few. Okay, the last ones always get a little, like, you have to really jog your memory on some of that stuff. But those will come into play. All right, let's get into 6.2 because that's
it?
Yeah, that's all I'm doing for 6.1. Okay, so 6.1 practice, it's really review of this. But you can't do 6.2 without knowing how to do 6.1, but I just didn't want to spend a lot of time on 6.1 because it's literally the basics of integration. Okay, 6.2 is not. So now we jump right into reverse chain rule and u-substitution. Now, one of the things I will tell you about this is some problems absolutely require u-substitution, okay? And other ones you can use u-substitution, but you don't necessarily have to. At the end of the day, what you should do is whatever you know is going to allow you to be successful. And if that means sort of overusing u-substitution, then do that, okay? If you feel confident in terms of doing some of that stuff in your head and you continuously get their answers correctly, then I'll give you some leeway there. But if you aren't 100% confident with trying to integrate some of these problems without using u-substitution, then don't try to do it. Use u-substitution. So obviously at some point we want to get to a place where we can move past that when possible. Sometimes it's just not possible, okay? All right, so this is what it boils down to. Like, how do you know? How do you know when to use u-substitution? It really is reverse chain rule, okay? How do you know when it is necessary? And I'm going to give you some information here. It's sort of my best way to help you figure out when you have to use it, okay? Now, I pulled something from the AB book. If you want to screenshot it from there, it's on page 413. This is the substitution rule, okay? The thing that's interesting about when you have to recognize the situation is there's usually some type of combination of a chain rule looking type problem, and then there's a derivative in there too, which seems counterintuitive because we're talking about integrals. But there will be this extra derivative of the inside function next to it, usually. Or it'll look similar to it. Okay? And that's when you know, hey, I probably need to use u-substitution here. I've got a reverse chain rule situation, okay? And so that's what you kind of want to look for. Now, we're not talking about constants. We're talking about some other polynomial function, a monomial or binomial or something, okay? There's going to be a relationship between the inside function and the polynomial that's being multiplied by it. And that's when you know you got to look for that and use that u-substitution, okay? So here's some kind of, there's not a hard, fast, black and white way, but there's some things that I can tell you that make it more probable. So I'm going to give you those little hints, okay? You're asked to integrate a product of polynomials, okay? So it's not just a polynomial, it's going to be a product of polynomials. That's one indicator that you're going to have to use u-substitution. And so notice my qualifying word, often. It's just not always. Often. Okay. That's the first kind of hint or tell. Okay. The next one that you kind of need to watch for. There may be polynomials to powers that aren't easy to simplify. And so what I'm saying there is like, for example, we can take a binomial squared and we can multiply that out pretty quickly, pretty easily, right? But if it's to the fourth power, generally you're not going to be asked to expand something like that. Okay? If the multiplication or the power is such that the polynomial raised to that power becomes really challenging, you probably shouldn't multiply it out. Okay? Doesn't mean you can't. It's just going to take you, it's going to be tedious and lots of opportunities to make mistakes. Okay. Another for is polynomial under a radical. That's pretty much a given that you're using u-substitution there, because you want to get that polynomial out and make it u to the half power, u to the 2/3, or whatever. And then you hope that there's an extra derivative of the radicand sitting there somewhere. I've got two more little look fors. Actually, the last one really isn't one. Trig functions might be thrown in there where it just feels random. It's like, what is that? Why is there a cosine there all of a sudden? This was a great looking polynomial, and then all of a sudden there's this trig function there. You're probably going to use that as your u, or some form of it. Like I said, the last one isn't really, it's just any of them combined together. Any combinations thereof, you're probably using u-substitution in these kinds of situations. Those are the best sort of hints that I can give you. Obviously, you know, when you're working on problems in 6.2, you're probably going to be using u-substitution, right? Because it's in there. But when you get to a test, when you get to the midterm, when you get to the AP exam, like, you have to know, like, to look for some of this stuff before you just try to figure it out. You know, ultimately, you want to get to a place, if you don't have to use it, to not use it because it will be quicker. 1. 2, because you have a level of understanding of the depth of these problems that you can sort of move past that. At the end of the day, however, if you want to use u-substitution because that's sort of a safe place for you and you feel confident that you can do it right every time that way, then use it. Usually what ends up happening with u-substitution is it takes a little longer if it's a problem that doesn't require u-substitution. Now I'm going to show you an example where I'm going to do it where you don't need u-substitution, but if you want to use it, you can use it. You're going to get the same answer the same way. Okay, and whichever one you're more comfortable with, that's what I want you to use, because obviously if you're comfortable with it, then you're confident about it, and you're more likely to do it right. Okay, now this is on 25. You can put it in from your book if you want. We talked about these already, but this is sort of what we went over on the left column is what we just went over 6.1. The u form of it, it's really the same thing. It has that added, why I highlighted that is what's added to it is the derivative of whatever u is. Okay, that's really the only difference between the left-hand column and the right-hand column. And that's, again, getting to this idea of what am I looking for to know that I have to use u-substitution. Well, there's going to be an extra term there that might not be there, an extra polynomial that might not be there. And that extra polynomial, most of the time, is the derivative of whatever your u is going to be. Now, of course, in the problem, there's not u's, right? Our u is going to represent x squared plus 3x minus 7, right? And then you're going to find that to the 7th power, or something weird like that, right? And then there'll be an extra, the derivative of that hanging around. So that's kind of how you know. All right, let's get into some problems. And we're going to do, let's see, 1, 2, 3? I think 3. No, 4. All right. Here's the first one. And these are all from your workbook too, so you can write them down or you can screenshot them. And I left the numbers with them. So this is number 6. Now this is one that you can use u-Substitution. Okay? This is also one where you don't need to use u-Substitution. And let me tell you how I know just by looking at the problem besides the fact that I've already done the problem. Okay? First off, which would be the possible u here? Would it be 3t squared plus 2t, or would it be t cubed plus t squared? Which would the possible u be? 1 or 2? 1. Which one would possibly be u? 1 or 2? 2. We have votes for 2. We have
I don't remember how to see it.
looks of amazement.
It's 2 because then you take the derivative.
Okay, so it has to be 2 because the derivative of 2 is 1. Right? The derivative of 2 is 1. Which means, because this is absolutely 100% the derivative of this, that's why I know I don't have to use u-Substitution. There's not anything sort of extra. The derivative of this is this. Okay? So, if I were to do this problem without, and here's the proof of it, right? Here's the step, right? The derivative of t to the third plus t squared is 3t squared plus 2t, which is this. Okay? That's how you know you don't have to use u-Substitution if you don't want to. Like I said, I'm going to show you how to do this with u-Substitution, and it's going to be fine. Okay? And so, essentially, all I'm doing is I'm taking this entire polynomial, and I'm treating it like one thing to the first power. Okay? And so in order to take the integral of that, the antiderivative of that, I'm going to use the power rule of this whole thing, because this part is already taken care of. Okay? So I'm really just using the power rule here, taking this, since it's to the first, it goes to the second, and then I have to divide by 2, and that would be my answer. Now, again, if you're not comfortable yet just jumping to that, okay, you can use u-Substitution, and my u would be t to the third plus t squared. Okay, I'm giving you 2 options on how to do this problem is what I'm saying. And I want you to use the one that you're more comfortable with. And so then, of course, after we've established what our u is, you have to take the derivative of both sides, which is, so du equals this. Well, all of this is already in my problem. So this is du. So essentially what I have is the antiderivative of u du. Okay, and so I go back to this idea then, okay, it's just power rule. U squared over 2. Well, of course, there's no u in this problem. There's a t squared plus, or t cubed plus t squared all squared. Now, quantity squared. Here's what the determination you have to make for yourself. So again, here's the thing, okay? I don't care which way you do it. If you are more confident and comfortable like this, then do it like this. Yeah, is there a couple more steps? Sure. Okay. But ultimately, what I want for you is to feel confident that you know what you're doing and you get the right answer. And if you're more confident doing it this way, then do it that way. Right? But the situation where you don't have to use u-Substitution, where there's a lot going on in the problem, is when the inside function, this derivative, is already there. The inside function here is t to the third plus t squared. This is the inside function. The derivative of it is sitting right there, which that's how I know that I don't have to use u-Substitution. If you don't want to go through the problem or hassle of doing that analysis, then don't. Just go straight to u-Substitution. You'll still get the same thing. Okay? All right, next one, number 9. All right. Now, so here's the thing with this problem. This problem by itself seems pretty innocuous. Like, meh, this should be pretty easy, right? Negative cosine 4x. Boom, done. Yeah, but what should there be? What would we expect there to be in this problem as well?
A plus C.
No, that's the very end.
Okay.
A what? A 4, why?
When you do the derivative, you get 4.
Yeah, there's the derivative of 4x. So my inside is 4x. There should be a 4 hanging out here somewhere. Okay? We should expect there to be another 4 there. But there's not another 4 there. Because the derivative of 4x is 4. So maybe you're thinking, okay, so what do we do? Well, we're going to manipulate. Here's some algebraic manipulation. Okay? We're going to put a 4 in there. Because you can do that, right? You can just throw a 4 in there, can't you? Just like this. Boom. Just put a 4 there. Can you just put a 4 there? No, you can't. Of course you can't just put a 4 there. No, but what can we do to counter that? Put a 1/4. Exactly. So what we do to counter that, again, this is algebraic manipulation. We're trying to get what we need. And so I can put a 4 in there, but I can't just put a 4 by itself there. And this is where that scalar multiplication comes in, right? 1/4 times 4, of course, is 1. We've done nothing besides change the way this looks. The value of the particular function hasn't changed. And the reason, again, that we did that is because since the inside function here is 4x, the derivative of 4x is 4, there should be a 4 here. Okay, but because there wasn't, we put 1 there. And then we countered it. Now, so this is the same kind of thing. This does not require u-substitution. Because the derivative of 4x is 4 and it's already there. Which means the antiderivative of 4 times sine of 4x is just negative cosine 4x. Because we're already taken care of with this derivative. Now, if you want to use u-substitution, you can. And you can say u equals 4x, du equals 4 times dx, and there's my 4 dx, and you're good. The only difference is I'm going to have this 1/4 that's just hanging out. It's going to be there the whole time now. Okay, so in this problem, I did not use u-substitution, but you could. Okay, and so since my 4 is already here, the derivative of my inside function, I can just say negative cosine 4x. That replaces all of this. I got my plus c. Probably need to clean this up a little bit, but it would also be fine if you didn't. But I'm going to, because you know me by now. That looks cleaner to me. Now, again, I didn't use u-substitution. You could. You could say sine of u and du is the same as 4 dx. And you could have done it like that if you wanted to, and then sub the 4x back in. You would still get the same answer, and you would still need the 1/4. Okay. Did I skip one? This is better. All right, here's the problem. I jumped ahead too quickly. Okay, here's the problem. Now, what I want to think about is this in terms of the last problem where we had that 4x as the inside. My inside here is y cubed plus 1. And the derivative, since we're talking about y, of y cubed plus 1 is 3y squared. Do you agree? So like the last problem, when we sort of expected there to be a 4, we expect there to be a 3y squared in front of that. Now, which leads to the next slide, right? Just like before where there was a 4 and then we did 1/4 on the outside, can you just put a 3y squared in here and then multiply it by 1 over 3y squared? That's what I was. Next one. Okay, here's number 8. Okay, so here's the question here. Right? And I should get rid of that for a second. Let me do that.
Wait, why you?
Yeah, no, I know, you're wondering why I'm asking. No, I know. Here's the, let me change something here real quick. Out with this. So could we, and I'll write it out for you. Can we do this? 1 over 3y squared, and then I would throw my 3y squared in there. Can you do that? Is the question that I'm trying to ask. Can you just put one of these out here like this? They cancel out, and now we can do the problem just like the last one. And can you do this? Is the question.
You can't take out the variable.
Correct. You can't take out a variable. This only applies to scalars. Okay. So the answer I was getting at was no. You can't just do that. So don't think you can do what we did on the last problem because it's a variable. When variables are involved, the rules are different because that scalar multiplication thing only involves scalars, which are constants. Okay? So, the point I'm trying to make here is, do you have to use u-substitution here? Or can you kind of skip past that? If you could do this and multiply by 1 over 3y squared, and then throw a 3y squared in there, then the answer would be no, you don't have to use u-substitution. But because we can't do that, that's our only option. So we absolutely have to use u-substitution for this problem. Okay? Or you have another option. Can you multiply this out?
Yeah.
Yeah, but why would I want to?
Would you rather do u-substitution than multiply it out? This is just a binomial squared, right? You know the rules for binomial squared now. And if you still don't, multiply it out. But this is this term squared, multiply them together times 2, this term squared. Right? It's the Batman meme. The old Batman meme.
I noticed your square root one.
Square root 1 is a new one, courtesy of Andrew Pino. That's the Andrew Pino sent that to me. Yep, the square root 1. We got a new one. All right, so I'm going to multiply this out. Because when you multiply it out and you just have a regular polynomial, then integrating that's pretty simple. Okay? So when you multiply that out, here's what you get. Okay? Square the first one, y the sixth. Multiply them together times 2, square the last one. Finish it. And actually, this is the reason we can't use u-substitution either, because there needs to be a 3y squared. Even if I made u equal y to the third plus 1, I'd still need a 3y squared somewhere, or a y squared at least. And there's not an extra y somewhere. So this is actually my only option. Now that we talked that all out. All right, and then this is easy, right? Maybe it gets a little trickier in here, but not that much, okay? So y the 7th over 7. Y the 4th over 2, let me write in my little work here in case you didn't see this. So this is 2y to the 4th over 4, which simplifies to y to the 4th over 2. And then, of course, this is y, and then don't forget your c. Okay? I think I have one more example. Nope, I have 2 more. Sorry. Yep, 2 more. Problem. The reason you can't use u-substitution here is because it requires the derivative of the inside function to be there, or at least part of the derivative. And the problem before, the part of the derivative was a constant. The derivative of this has a y in it. It's 3y squared. Okay? There's no extra y sitting out here. And since I can't divide by a y on the front, that's how I know u-substitution is not going to be applicable here. Because I don't have the extra y, because the derivative of the inside function, or at least part of it, has to be there. But the variable part has to be there. In this problem that we just went through, okay, we're going to fly through these, I hope. Okay. So, here's the thing. I've got polynomial multiplication. Yeah, you have to use u-substitution here. You have to, okay? Because what's my u? What is my inside value? My inside function? X minus 1. And again, I mentioned the radicals. So u equals x minus 1. but I have an x dx here. Okay, and I have an x. I'm going to have to replace an x. So I really need to get this x by itself first, because eventually I'm going to have to replace the x. So let's slide the 1 over. Then you can differentiate it, right? So that takes care of my du and my dx are the same. When you differentiate this. Because I have this x here, because eventually I'm going to substitute u plus 1 in for x. Okay, so here's what I've got. Several things. One, x is u plus 1, so I can replace this x with u plus 1. This is u, and then since du equals dx, I can just make that du. So here's where I'm at. And maybe you're wondering, well, why did you asked me this, why did you move the 1? Why did you make it u plus 1? Because I only have an x here. So I'm replacing, so I have to get x by itself in order to substitute in for x. Okay, what am I going to do here? Yeah, just going to multiply it out, distributive property, right? So u times u to the 1/2 is u to the 3/2. Okay. So here's where I'm at. And then again, it's just product rule from there. And then I'll sub back in x minus 1, and we'll be done. Okay. So this, add 1 to this, that's going to give me 5/2. Add 1 to this, it's going to give me 3/2. So you divide by that is the same as multiplying by the reciprocal. It ends up giving me 2/5 times u to the 5/2, 2/3, because originally it's u to the 5/2 divided by 5/2. And then I just have to sub the u back in, and we're done. Again, here's the thing. The reason on the last problem, just to keep us straight, on the part of the derivative of the inside function is here, okay? Because it's to the 1/2 power. All right, move on, last one. Okay, so again, my inside function, what's my inside function here? 2x plus 3. Now I have the derivative of 2x plus 3 is x. And I have an extra x. Even though there's other numbers associated with it, that's okay. We don't need to worry about that. But because it has that extra x, you absolutely have to use u-substitution. Okay. So what is my u? 2x plus 3. Okay. And now I got to simplify this down somehow that's going to be useful to me. Okay. And so you've got some options. But I can get the 2x by itself, which means I already have a 2x. So why don't I just slide the 3 over? And now I have a place to substitute the u minus 3. Now you're saying, okay, what does that affect the derivative? No, it doesn't. Okay, because the derivative of this side is just du. What about this side? What's the derivative of this side? 2dx. Okay, so now we have a little bit of an issue, right? Because I'm already going to substitute in for the 2x. So what I need to do is get the 2 to the other side so that I have just dx by itself. And so what ends up happening is I'm going to substitute this dx, I'm going to substitute 1/2 du in for it. Now we're set up, we've got everything done. And it's just a matter of plugging stuff in and finishing it up, okay? So I'm going to try to go fast. So my 1/2 for the du, I just slid it out front and we can ignore it, okay? This u minus 3 goes in for the 2x, and I have the minus 1, and then I decided to bring this up, make it u to the negative 9, okay? And then I'm going to multiply this out eventually. So if you want, I'm going to go to the end. So if you want to write the down if you want to finish it up, but yep. So all I did here is I simplified, then I distributed, just like we did in the last problem, and then I did regular product rule. That half is still hanging around. I distributed it here, and then we resubstitute it back in. Okay. So yeah, take a picture of that. Spend a little time with that later. You've got homework over the weekend, for many of you, the 3-day weekend, practicing this, and then we will also spend time on Tuesday working on this again.